Let's say I have a system of equation with the augmented matrix A and the vector B here. And let's say my matrix A here, let's say this guy, this is an m by n matrix. So my matrix will have m rows and will have n columns. So then I can kind of think of this matrix A as just a bunch of vectors. So I'm going to have a bunch of vectors here. So what that means is because my A is an m by n matrix, so I'm going to have n vectors here. And each of my vectors is going to have m coordinates. So n is going to be the number of columns of A, and that's going to correspond to the number of vectors that I have. So my n is going to be the number of vectors. And my m, this is going to be how many digits or how many coordinates each of my vector has. So m is going to be the number of coordinates. Let me actually write this number of coordinates. And we have seen in the last example that if the system is always solvable, whenever I can guarantee that the system is solvable, then what that would mean is the vectors that I have here, each of the little blue vectors that I have here, is going to span r to the m. So m here, this is going to be the number of coordinates that I have. So in my earlier example, m is going to be 3 here. Each of these little guys has 3 coordinates. So all these 4 vectors together. So here, let me actually say my n is going to be 4, and then my m is going to be 3. So all these 4 guys would altogether span r to the 3. 3 is m, which is the number of coordinates. However, we also see earlier that one thing that would guarantee that my system of equation here is going to be solvable. We see this in the example 2.1. Let me actually write this back. So we see this in example 2.1. One thing that would guarantee that this system of equation is going to be solvable is when the rank of my matrix A is equal to m. So whenever the rank of my matrix A equal to m, that means I can guarantee that all these little vectors that I have is going to automatically span r to the m, and that's kind of what we have here. Whenever I have n vectors, I can use those to form a matrix A, kind of like what we did up here. If the rank of this matrix is m, then I can automatically guarantee that all these vectors is going to span r to the m. For example, if I were to look at the example down here, I'd like to see if this vector 1, 0 and 0, 1 would span r square. Now you can actually kind of see that this is actually just the standard basis for r square. But if I were to use what we have up there, I can use this to form a matrix 1, 0 and 0, 1. And indeed, the rank of this guy is going to equal to 2. So because 2, this is the same as the value m that I have up there. So m here is going to be 2. So then I can guarantee then that this guy is going to span r square for sure. It's going to span r square for sure. In other words, if I were to solve the system of equation 1, 0 times x plus 0, 1 times y equal to ab, for whatever value of a and b are, I'm going to be able to solve this for sure. I'm going to be able to find x and y for sure. And you can kind of easily see that the x is going to be just the value of a, and the y here is going to be just the value for b. Now for part b, I can once again form a matrix 1, 0 and 2, 3. And then the rank of this guy is once again going to be 2. And we actually kind of have done this in one of the earlier examples. This was in the example 1.7. So once again, I can guarantee that this guy is going to span r square for sure. In other words, if I want to solve the system of equation 1, 0 times x plus 2, 3 times y equal to ab, for whatever value of ab, for whatever vector that you throw at me in r square, I'm going to be able to find x and y such that this vector is a linear combination of the 2 vectors that we have. Now, if we were to look at the next one, I only have one vector, 1, 0, and you can probably think, so intuitively, if you only have one vector, I should not be able to reach all the points in R square. So intuitively, this should not span R square. Or if I were to check, I can basically just form a matrix. It will just be a 2x1 matrix. This is already in row echelon form, and the rank of this guy. And the rank of this guy is 1. Notice that the rank here is less than the value m that I need. So this guy will not span R square. In fact, I can actually make an observation that whenever the number of vectors, which is n, is less than m, so once again, n is the number of vectors and m is the number of coordinates. Whenever the number of vectors is less than the number of coordinates, then these vectors are not going to span R to the m for sure. Another explanation is that we have seen in example 1.8 that the rank of the matrix has to be less than or equal to the value n. So, if n is less than m, what that means is the rank of the matrix, well, it has to be less than or equal to n, but n is less than m. So, the rank of the matrix will not equal to m for sure. And what that means is my vectors v1 to vn cannot span for sure. Yeah, if I don't have enough vectors, then those will not be able to span R to the m for sure. However, more doesn't mean better though. For example, if I look at part D here, even though I have 10 vectors, but all these guys are just multiple of 1, 0. In fact, if I were to look at the matrix, I just put all these together. 1, 0, 2, 0, 3, 0, to 10, 0. This is already in reduced row echelon form. The rank of this guy is actually just going to be 1. Yeah, so even though I have 10 of these, they actually doesn't do any good. So this guy will not span R square.